Okay, then now let's take a look at Kepler's laws. And Kepler was an astronomer, and he came up with 3 laws about the motions of planets. Okay? So his first law says that every planet moves in elliptical orbit with the sun at one of the focal points. Okay? So again, we'll take a look here. Remind you about ellipses. Right? So we have an ellipse like this. The axis that makes the longest part of it is called our major axis, and then we have the minor axis. So the major axis has a distance s, and basically the deal with ellipses is that the focal points, if we add the distance to any point here from one of the focal points, the distance from any point from the same point back to the other focal point, if we add those two together, they remain constant. Okay, so the total distance, d1 plus d2, is equal to a constant. Now, a circle, which most of the time before we were talking about circular orbits, is just a special case of an ellipse where the two focal points are in the same position. Okay, and then every point here, still this is true. Okay, so let's take a look at this flash again. And this time we have a planet and a comet, and the comet's going to go around in a elliptical orbit, whereas the planet's going to go around in a more spherical orbit. Okay, so an ellipse with the sun at one of the focal points. The other focal point would be way out here. This one's closer to a circle, so both the focal points are all at the same, or in the same position. So that's Kepler's first law, that every planet moves in elliptical orbit with the sun at one of the focal points. Now, his second law, so Kepler's second law says a line drawn from the sun to the planet will sweep out equal areas in equal periods of time. Okay, so in our orbit of ellipse around the sun, a planet here will sweep out, say, this much over a particular amount of time, whereas a planet way out here will sweep out this much in a particular amount of time. Okay, but the areas of these two, where I filled in here, will be equal to each other. Okay, so what that means is that when the planet is close to the sun, right, it has to go much faster so it can cover the right amount of area, and when it's farther away from the sun, it goes much slower, so that these areas here will be equal to each other. And we'll actually derive this later when we get to angular momentum. Okay. Now, Kepler's third law seems to be a formula here. T1 over T2, that ratio squared. S1 over S2, that ratio cubed. Remember, S1 and S2 have to do with the ellipse, and that's the major axis of the ellipse. Okay. Now, this formula here can actually be derived from Newton's gravitation. And to make it a little simpler, I'm going to assume that we have a circle instead of an ellipse, so that our S1 goes to radius 1, and our S2 goes to radius 2. Okay. Now, this formula actually has to do with two bodies rotating around the same sun. So, say, Mars and Jupiter. Okay? So this is the period of, say, Jupiter around the sun, the distance it is away from the sun. Okay? And then this is, say, the period of Mars around the sun, and this would be the distance away from the sun. Okay, so we can use the ratios of the periods and the ratios of their distances away from the sun. Okay, all right, back to deriving this from Newton's gravitation. So Newton's gravitation says the gravitational constant times the mass of the orbiting body times the mass of the sun over the distance it is away from the sun squared is equal to the mass times the radial acceleration. Okay, and again we know that radial acceleration is v squared over r. And again I'm going to use our velocity as 2 pi r over the period and plug that back in for our velocity here. Okay, so we get g equals the mass of the satellite or planet or whatever, mass of the sun, r squared, and this becomes 4 pi squared r, 4 pi squared r over the period squared. Our masses cancel out, so it doesn't matter what the mass of the satellite is. And moving things around, we get T1 squared over R1 cubed. Okay. Now, on the other side of the equation, that ends up with 4 pi squared over the gravitational constant times the mass of the sun. Okay. Now, this side here, right, are all constants, right? The 4 pi, the gravitational constant, the mass of the sun, that's all going to remain constant. Okay. So we could go through this whole thing, and instead of doing R1s, we could do R2s. Instead of T1s, we'd have T2s. And we get the same formula, but with T2 and R2. Okay? So that means that T1 squared over R1 cubed would be equal to T2 squared over R2 cubed. Okay? And just moving that around a little bit, we get Kepler's third law. So on this side, we have the ratio of the period of two different objects rotating around, orbiting around one sun. And on this side, we have the ratio of their distances away from that sun. Okay? Now, we did this for the case of a circle, but it's also true for an ellipse. So this, the general form up here is true, and we can use this for any two orbiting bodies. Okay, and the next example I'll show, you'll see why this is, or how it's used and why it's used.